So today we're going to talk about finally getting into fracture. So fracture is the last resort of any material after all of your elastic, plastic, creep, everything other than the mechanism has been exhausted. So the energy considerations that you have to think about is when you fracture, you're creating surface area. But by creating surface area, you can also relieve basically the elastic strain energy in materials. So that is going to be your energetic competition when you look at whether a material will fracture or not. So that's how we're going to derive it, and we're going to use Orwan and Griffith expressions in order to do that. Similarly, the theoretical yield strength is much larger than the actual yield strength because of defects and specifically because of microcracks. So microcracks function as effective stress concentrators. So near a crack tip, you will see larger stress values occur. So we can derive actually what is the critical crack length for a material to fracture by looking at an energy competition between the surface area created versus relieving your stored elastic strain energy. So we can break it down into these two contributions, and we can actually see what's going to happen and how do we minimize the total energy of our system. So again, fracture will proceed if the relief is greater than the cost of forming that surface area. So I can look at my elastic strain energy, as we've done many times before. This is an energy per unit volume, so we need to multiply by the volume of our material, which is just going to simply be our thickness of material times the elliptical crack surface area that we'll see a little bit below in that microcrack. So you'll also notice that this is a negative energy because, again, we're relieving that elastic strain energy. That is a positive expression, or actually a positive energy, a favorable energy, so hence it's going to be negative, reducing the energy of our system. So good energy, favorable energy, negative energy. Creating surface area, on the other hand, will be positive. So again, it's the surface area, surface tension, surface energy of your system times the area, and then we can basically equate those, and then we see our expression for stress at fracture as a function of our crack length and our stiffness. That is good. That expression is good for brittle materials, but we also can use our Orwan expression for materials that are more ductile. You can also use a stress intensity fracture toughness. So this is an empirical expression which tells you the inherent fracture toughness of a material, and you could relate that based on the stress applied and then the initial, your crack size. So there are different crack modes as well in your materials, so modes 1, 2, and 3. In addition, we talked about essentially our Orwan criteria that's good for ductile materials because there will be a plastic zone of deformation before the crack extends. So if our radius of plastic zone over our crack length is less than 0.02, the Griffith criteria is good. If not, we want to use the Orwan expression. And we can actually calculate what will be that radius of our plastic zone by equating some of the expressions that we developed earlier. So looking at the yield strength in terms of our fracture toughness, and we have our expression to calculate the radius of our plastic zone, or our zone of plasticity, if you will. So again, taking that expression, plugging it back in, and now we can calculate it and see which mechanism or see which criterion is basically more accurate, more effective at predicting fracture. Because that's what we're really trying to do here. We're trying to make sure that basically our fracture, captures the real behavior of our material. There are lots of different mechanisms by which fracture can occur. You could have some very, very brittle fracture that propagate quite easily, especially in ceramics. Fracture is inherently stochastic. Some metals will basically fracture more ductilely. For polymers, they can be very, very ductile. But again, it just depends. There's usually some type of plastic deformation prior to fracture, unless you're dealing with extremely brittle glasses and ceramics. Temperature can also drastically change how, especially polymers, will fracture. Some materials also undergo a ductile to brittle transition based on temperature and other considerations as well. So that can be very harmful, and it was very harmful in our Liberty ships. You can fracture via creep too, intergranularly. So typically, they'll fracture along those grain boundaries, and we could try to prevent crack, basically the propagation of a crack by blunting that crack tip with inclusions or precipitate particles as well. So that is a way to increase the toughness of your material and try to avoid fracture and even self-heal if you have microcapsules. See you next time.